Let's talk about induction and exhaust systems. And by the way, isn't that a sweet sound? I don't think there's anything sweeter than the sound of a P-51 Mustang firing up. And a lot of that sound, as you know, is due to the induction and exhaust systems of this aircraft. And isn't that a nifty lead into this subject? Let's talk about induction and exhaust systems, and particularly we'll lead off by talking about induction systems and problems associated with them, icing for instance. The FAA wants you to know some things that are very basic about an aircraft engine, and you probably already know these things, so let's you and I count this as review. Let's review very fundamental things. First of all, as you know, when an engine is running, on the intake stroke, the piston goes down, the intake valve opens and sucks in the fuel-air mixture, and that creates a reduced pressure in the intake manifold. If you open the throttle valve, that pressure will increase again back to closer to, we'll say, ambient air pressure. So they're going to ask you on the test, as manifold pressure increases in a reciprocated engine, what's the effect on the density of the air in the cylinders? And the answer is, of course, as there gets to be more air pressure into the intake manifold of the engine, manifold pressure, the density of the air in the cylinders increases. They're also going to ask you, what's the action of the scoop in the front of the engine here, at the very front, they call it the air scoop, carburetor air scoop. Well, it's a real easy answer. The action of a carburetor air scoop, the purpose of it is to supply air to the carburetor. But it may also increase the pressure of the incoming air by ram effect. In other words, on some airplanes, as the airplane goes through the air, it rams the air in the front of the intake system and increases the manifold pressure very, very cheaply and efficiently, kind of a cheap man's turbocharging. So the carburetor air scoop can supply air to the carburetor and provide ram effect. Now, sometimes, if you want to increase the vaporization, make sure that the fuel-air mixture is totally vaporized, you can increase vaporization by circulating the fuel and air mixture through passages in the oil sump on the way to the cylinders themselves. So on small aircraft engines, you need to know fuel vaporization may be increased, and I'm giving you FAA magic words here, by circulating the fuel and air mixture through passages in the oil sump. Now, let's talk about leaning the mixture in an engine. Of course, on almost all piston engine aircraft engines, you can lean the mixture by pulling on the mixture control, and you reduce the mixture for thinner air at higher altitudes. So you have the same relative ratio at high altitudes as you do at low altitudes. And that ratio, of course, is by weight. Now, they're going to ask you what will happen if you have an excessively lean mixture. Very basic question. The answer is you could get high cylinder head temperatures from an excessively lean mixture, and that's just by pulling back too much on the mixture control at higher altitudes. They're also going to ask you about the carburetor air intake heater. And here we have one here, and it's basically the heat box, and it heats the air going into the carburetor. If we take a look at our drawing again, we'll get a little better look at that. You can see here we have the exhaust system and a muff around the exhaust system that circulates intake air past this exhaust system without mixing with the exhaust system. And when you select carburetor heat, the air gets supplied unfiltered, heated air to the carburetor. On the other hand, if you don't select carburetor heat, then the air that gets supplied to the carburetor goes through this filter, but it's colder air to the carburetor. Of course, the reason you supply carburetor heat is to make sure you don't have icing inside the carburetor itself. This is supposed to be a carburetor up here, by the way, right up there. Okay, so a carburetor air intake heater, which removes ice from the induction system, usually derives its heat from what source? And the answer is it normally gets its heat from exhaust gases. Now, the exhaust gases don't go through the engine, but it does get its heat from the exhaust system or exhaust gases. So that's the question they're going to ask you on the test. And they're going to say, all right, let's assume that a pilot comes and says, oh, look, I'm not getting full power on takeoff. What could be one of the problems? And the answer is the linkage here in the carburetor heat valve, this butterfly valve, could be allowing carburetor heat to be heating the intake of the engine on takeoff. So a factor in the failure of an engine to develop full power at takeoff could be due to improper adjustment of carburetor heat valve control linkage. In other words, some of the air going into the carburetor is hot air when you're trying to take off, and of course reduces the performance of the aircraft. Okay, so would you normally use a carburetor heater, preheater they call it, preheat for the carburetor on takeoff? And the answer is no, not unless it's absolutely necessary, because you do have loss of power when you have hot air going into the engine. The reason for that is the air is less dense. Also, the mixture gets a little richer because the air is less, the fuel stays the same, so the mixture gets richer. So a carburetor preheater is not generally used on takeoff. Plus, it's absolutely necessary because of a loss of power and possible detonation. If you put hot air in here, you're more likely to have detonation of an engine. Now, when operating an engine, the application of carburetor heat will affect the fuel-air mixture. How? Well, if you apply carburetor heat, when you put the carburetor heat on, as I said earlier, it enriches the mixture control until the automatic mixture control on some engines can make a compensation and will decrease the weight of the fuel-air charge. But generally, what you need to know is that when you apply carburetor heat, you enrich the mixture in the engine. Should you use carburetor heat like this when it's not needed? No, the answer is no, you don't want to, because you, as we said earlier, have a decrease in power and possible detonation. So you only use carburetor heat when you think there is an icing situation possible. Now, let's assume you want to start this engine and it's equipped with a carburetor air heater. Should you start the engine with a carburetor heat in a hot or cold position? Well, the answer is anytime you're operating on the ground, you want the carburetor heat in the cold position so that you have filtered air going to the engine. Otherwise, the air is unfiltered. So you start the engine, operate it on the ground with the carburetor heat in the cold position. Now, let you and I talk about superchargers and turbochargers. And boy, here's a beautiful example of an airplane that has supercharged engines, a B-29. It's a beautiful airplane. All right, they ask you a few questions about superchargers and turbochargers on the test. Let's talk about how they work. And the idea of both of these, by the way, is to compress the air going into the engine so you have higher manifold pressure than you would if you didn't have them. The way a turbocharger works, and we'll talk about that first, then we'll come back to a supercharger, but the way a turbocharger works is you drive that compressor to compress the air going into the engine with a turbine that's driven by exhaust gases. Let's take a look at it. First of all, you have exhaust gases coming from the cylinders of the engine. They're collected in the exhaust system, and they're driven by this turbine that spins this turbine. Of course, the exhaust goes out the exhaust pipe after it spins the turbine. The turbine spins the compressor, and the compressed air compresses the air going into the intake manifold of the engine. That's a turbocharger. By the way, if you have a turbocharger equipped on an aircraft and you don't want to turbocharge at the time, you have a wastegate down here in the exhaust system. You open this wastegate, and the exhaust, instead of running past or through the turbine, goes around or bypasses the turbine because the wastegate's open, and that's the easier route for the exhaust gases to flow. And so you bypass the turbine, and then the air goes out without spinning the turbine, or the exhaust goes out without spinning the turbine. But if you do want to turbocharge, then you close the wastegate, or partially close the wastegate, depending on how much you want to turbocharge. But you close this wastegate, now the exhaust gases are forced to go past the turbine, spin the turbine, and that spins the compressor that compresses the intake manifold of the engine. So this is a turbocharger. We'll talk more about that, but that's the basic design of a turbocharger right there. Now, they ask you just one or two, maybe, questions about superchargers on the FAA written exam, so you need to know what a supercharger is. Well, a supercharger does exactly the same thing. It compresses the air going into the engine, and actually it compresses the air after it's mixed with fuel, but that really doesn't matter. It's not a question they ask you, but it compresses the fuel-air mixture going into the engine. But the difference is the way a supercharger impeller or compressor is driven, and it's generally driven by being connected directly to the engine. We'll say the crankshaft or the camshaft of the engine, so it's connected directly to the engine and with a gearbox in between, and that supercharger then compresses the air, but instead of being driven by exhaust gases, it's driven by the engine itself. Sometimes they'll have a gearbox on a supercharger, so you can select either high-speed or low-speed impeller. And if you don't want to supercharge a lot, you'll select low-speed impeller, and if you want to supercharge an awful lot, put a lot of increased manifold pressure there, you'd use then high impeller in that particular case. They're going to ask you about switching from low to high impeller on the FAA written exam, and you're sitting on the ground, for instance, about ready to fly your Constellation, and you want to check to make sure that the supercharger is working right, so you shift gears in the supercharger. You shift from low to high impeller. Now, they're going to call this on the test a single-stage two-speed supercharger. They're going to say, all right, super mechanic, you shift from low impeller to high impeller during a ground check. How do you know it's working properly? Well, if it is working properly and this impeller speeds up, the manifold pressure would increase. And because you're doing a ground check and you're basically in a fixed pitch portion of the prop because the governor is not working because you're not enough RPM, you would also have an increase in RPM. So when you switch from low impeller to high impeller in a supercharger on the ground during a ground check, you'll have an increase in RPM and an increase in manifold pressure. And just to confuse you a little bit, to ask you about this, you'll also have a momentary drop in oil pressure because oil pressure is used to switch from low impeller to high impeller. That's it. That's the big question to ask you on the test about superchargers right there. But they are going to ask you some more questions about turbochargers. One of the questions they're going to ask you is, how is a turbocharger driven? What drives? What's the power for a turbocharger? And by the way, they call these turbo superchargers or sometimes externally driven superchargers. And so a turbocharger is called an externally driven supercharger or a turbo supercharger on the FAA written exam. They're the same thing. A supercharger is called an internally driven supercharger. So both turbochargers and superchargers, according to the FAA, are superchargers. If it's internally driven, it's what we call a supercharger, and it's driven by the engine itself. If it's externally driven, the FAA calls it a turbo supercharger or an externally driven supercharger, and it's what we call a turbocharger. And what drives an externally driven supercharger? And the answer is exhaust gases driving a turbine are used to drive an externally driven supercharger. So on the test, if you see something called an externally driven supercharger, what in the Sam Hill is that? And the answer is that's a turbocharger. That's what everybody else besides the FAA calls a turbocharger. They're going to ask, okay, now let's assume you do have a turbocharger. What is the purpose of a turbocharger system for small reciprocating aircraft engines? And if an engine like that would be a 414 is a good example of an engine with a supercharger that is actually a externally driven supercharger called a turbocharger. What's the purpose of it? Well, the purpose of it is to compress air to maintain manifold pressure constant from sea level to the critical altitude of the engine. So very often all you're trying to do is compress air as you go to higher altitudes to maintain the constant manifold pressure. Now the manifold pressure may be higher than ambient, but what you're trying to do is keep a constant manifold pressure as you go to higher altitudes. It lets you increase the manifold pressure as you go higher. Now, what is boost manifold pressure? Well, boost manifold pressure is considered to be anything more than 30 inches. Now, if ambient manifold pressure, ambient air, is 29, 30 inches. So if you have manifold pressure higher than 30 inches, that is a magic word. That is called boost manifold pressure. It's manifold pressure above 30 inches in mercury. All right, now let's take a look at, once again, at a typical turbo supercharger. What is that? That's just a regular supercharger. They're going to ask you, what are the three basic parts of a typical turbo supercharger? Let's take a look at those three basic parts. They are the compressor assembly, that's right here, the exhaust gas turbine assembly, that's this part over in here, and the pump and bearing case, the whole case around those. And they're going to ask you about that on the test. What are those parts that are the three parts that are typical of a typical supercharger for a large reciprocating engine? And it's the compressor assembly, the exhaust gas turbine assembly, and the pump and bearing case, the case that goes around the whole thing. All right, now they're also going to ask you, what is the purpose of a wastegate? Well, a wastegate regulates the speed of a turbo supercharger. What is a turbo supercharger? That's a turbocharger. So a wastegate regulates the speed of a turbo supercharger. Now, many times you already know this stuff, but they ask this in such a funny way, what is a turbo supercharger, that sometimes you miss the question just because you don't know their terminology. All right, now here's what they're going to say also about this. If an engine equipped with an external turbocharger, that's the same as a turbocharger, an external turbocharger, and the wastegate is closed. Now, and you take off with the wastegate closed, or start the engine with the wastegate closed, what's likely to happen? Well, if you have this wastegate closed, you've got the turbocharger running like the devil, and you could have serious damage to the engine because of an overboost, because you're directing all of the exhaust gases through the engine. So if you start an engine with the wastegate closed, you could forget that you have the wastegate closed, and you could overboost the engine. And that's one of the dangers they're talking about that. I happen to know about that from experience, because one time in a Ray J system, you had a manual control of this wastegate in an airplane we were flying. We took off with the wastegate completely closed, by accident, by the way. Got about 50 inches of manifold pressure. It was an old Ray J converted 210. You talk about an airplane climbing. It climbed like a bandit for about a minute and a half. And then the engine started detonating, and we had real problems on our hands. So don't take off with the wastegate closed. It can cost you a lot of money. That's what they're telling you right there. All right, now let's take a look at a couple types of systems they have. One is a sea level boosted system, and we need to explain how the wastegate is controlled. Now the difference in these systems we're going to talk about a sea level boosted system, and we're also going to talk about a normalized, turbo normalized system. The difference between those two systems is how the wastegate is controlled. We'll talk about that. By the way, the definition of a sea level boosted system is one in which you have boost on takeoff. In other words, more than 30 inches of manifold pressure on takeoff. It's called a sea level boosted system. If, on the other hand, all the turbocharger does is keep the manifold pressure somewhere around 30 inches or less as you climb up to higher altitudes, it's called a turbo normalized system. And what a turbo normalized system does is it makes the engine think it's breathing sea level air even though it's at higher altitudes. Let's talk about the design of a sea level boosted system. Now the parts to a sea level boosted system, and we'll talk about these, are an exhaust bypass assembly, that's the wastegate, a density controller, and a differential pressure controller. Now, they're going to ask you what are those parts. You need to know that. The exhaust bypass assembly, that's the whole assembly for the bypass, including a wastegate and an actuator for the wastegate, a density controller, and a differential pressure controller. Now, let's talk about what each of those does. First of all, the density controller says, we don't want to have any more than, and you name a figure designed in the engine, we'll say 34 inches of manifold pressure. And if the engine has 34 inches of manifold pressure or more, it will open the wastegate. That's what a density controller does. It opens the wastegate if you start to overboost the aircraft. All right, the differential pressure controller is an elegant device, and it's what we used to have in a Cessna 340 that had a turbocharged system. Let's take a look at the differential pressure controller. Now, the way the wastegate is actually opened and closed, by the way, is not by hand in this turbo boosted system. The wastegate is opened and closed by oil pressure. And whenever there is oil pressure in this cylinder, it makes the wastegate close. And there's a piston here that does that closing of the wastegate. You can see it right here. Now, if there is no oil pressure in the cylinder, then the wastegate opens. Now, what you have is a differential pressure controller up here, and that's what I want to talk about. And the differential pressure controller it senses the pressure just before you get to the throttle valve and the pressure after you get to the throttle valve. And it says, look, I want there always to be, and I'm going to make this figure up, 2 inches of manifold pressure difference between the air pressure before you get to the throttle valve and the air pressure after the throttle valve. That differential pressure controller maintains 2 inches difference between the two, and here's the way it does it. If the difference gets to be greater than 2 inches because the throttle valve is closed or partially closed, then this controller will sense that. We're talking about the differential pressure controller. It senses more than 2 inches difference on either side of the throttle valve. When it senses that, then it will relieve oil pressure and open the wastegate, so that the turbocharger does not run as hard, and now you only have 2 inches of pressure between the two. This system also, the pressure differential controller, also prevents you from having bootstrapping, the turbocharger going up and the turbocharger going down, and the whole engine picking up RPM and dropping off on RPM and manifold pressure, because it tends to stabilize because it maintains that 2-inch difference. So this pressure differential pressure controller tends to eliminate bootstrapping. We'll talk more about that on a question later on. So you have a differential controller, and when the difference gets to be too big, there's too big a manifold pressure drop, it bleeds air off of this actuator, oil pressure off of this actuator and opens the wastegate, and so that the turbocharger doesn't work as hard. If there is not enough difference in the air pressure on either side, there should, we'll say, be a 2-inch air pressure difference on either side of the throttle valve. If it doesn't sense that, then it stops bleeding off the oil pressure from the wastegate actuator and closes the wastegate and speeds up the turbocharger, and that's the way that whole system works. Density controller does exactly the same thing. We talked about the density controller. If you start to go over the manifold pressure that the engine is allowed to have, we'll say 34 inches, the density controller will bleed off oil from the wastegate and open the wastegate just to slow the turbocharger down. That's how those two things work. All right, now let's take a look at the questions they're going to ask you about this on the test. First of all, they're going to say, what is the purpose of the density controller? Well, the purpose of the density controller in a turbocharged system is to limit the maximum manifold pressure that can be produced by the turbocharger at full throttle. That's the one that says, the density controller says, look, this system is not built to take any more than 34 inches of manifold pressure, so if it starts to go over 34 inches, it's going to bleed oil pressure off from this piston and open the wastegate. That's the density controller. So now let's take a look at what is the purpose of the differential controller. Well, the differential controller does something different, and that's the one that measures the pressure on each side. So the differential controller is this one that measures the pressure on each side of the throttle valve, and what it does, it functions during all positions of the wastegate valve other than the fully open position. It's constantly working except when you're fully open and then the wastegate closes and then you're driving the turbocharger as hard as you can. Now here is something that can happen in a turbocharged airplane that's considered to be a bad thing. It's surging, and this surging is caused by what they call bootstrapping. Now, to talk about what bootstrapping is, let's take a look at the idea of operating a turbocharged engine with the wastegate completely closed. Now what would happen is you're flying along, and let's assume you get into a little turbulence, and all of a sudden the engine runs just a little bit harder because there's more air going into the engine. What's going to happen is more air will go through the engine and actually through the exhaust system. You'll have more exhaust, and that will speed up the turbocharger. That would in turn pump more air into the engine, and that would speed up the turbocharger, and you get all of a sudden what you would call a bootstrapping condition. The FAA refers to it as a transient increase in engine power. And basically the pilot's getting fluctuations or surging that he's not commanding. Now how do you get rid of that problem? Well, you do it by actually controlling the wastegate, having it move back and forth to keep the manifold pressure the same, and that's the job of the differential pressure controller. So they're going to ask you on the test, what does the differential pressure controller do? Well, it helps prevent bootstrapping, and what's bootstrapping? It's that transient increase in engine power, otherwise known as a surge. A turbo-normalized system is one in which you just keep ambient manifold pressure at sea level all the way up to higher altitudes. It makes the engine think it's at sea level even though it's really at a higher altitude. Now, there is a different set of controllers in that engine then. You have an absolute pressure controller, and what it does is it says, look, we're going to put, we'll say 29 inches of manifold pressure on this airplane at all times before it gets to the throttle valve, the upper deck. So we're going to have 29 inches of manifold pressure before you get to the throttle valve all the time, and we're going to run this compressor hard enough to always maintain, we'll say, 29 inches manifold pressure. That's called the absolute pressure controller, and it does the same thing. It either bleeds or does not bleed oil pressure off the wastegate controller, off the wastegate actuator there. All right, now what is the purpose of a rate of change controller? Well, if you have a turbo-normalized system, you also have a rate of change controller, and what it does is controls the rate at which the turbocharged discharge pressure will increase. It just will not allow the turbocharger to increase or decrease rapidly. That's the rate of change controller. It just smooths things out. That's actually part of the density controller. All right, there is another thing in this system where we're talking about a turbo-normalized system, and that is called the pressure ratio controller. And it says, look, we don't ever want the ratio between deck pressure and ambient air, the outside air pressure, to be more than 2 to 1, because you'd be overheating the air, compressing it too much. This system is designed to only take so much. So the pressure ratio controller limits the ratio between upper deck pressure and ambient pressure. Here's the upper deck pressure right in here. Ambient pressure is outside the aircraft, and it says we never want to compress this air any more than a 2 to 1 ratio, and so you have that the pressure ratio controller, and once again it bleeds oil off of the wastegate actuator to open the wastegate, and that's the way it works. So they're going to ask you on the test, what is the purpose of a pressure ratio controller in a turbocharger system? And it's to control the position of the wastegate, and that's the wastegate right here, after the aircraft has reached its critical altitude. And the reason for that is the turbocharger will start working real hard when the airplane has reached its critical altitude. Ambient air pressure drops off, and it's much, much less. And the pressure ratio controller limits how much ratio of boost. We'll say a 2 to 1 boost is all it will allow over ambient, and it limits that so that you're not overheating the turbocharger and having too hot air going into the engine. All right, now let's take a look at a few miscellaneous supercharger questions they're going to ask you and turbocharger questions. They're going to say, let's assume that you put an intercooler right here and you cool the air going into the intake of the engine. In other words, you've compressed the air with either a supercharger or turbocharger. And now you have a heat exchanger called an intercooler, and you take air from the slipstream of the aircraft that's cold because it's cold outside at high altitudes, and run it past, without mixing them, but run it past this hot air that's just been compressed from the turbocharger or supercharger and cool it down. That's called an intercooler. What would be the purpose of that? And the answer is to cool the air entering the carburetor from a supercharger. If you had it on a supercharger, it would be on a supercharger. Speaking of Bernoulli, let's talk about an elegantly simple device called a sonic venturi. And a sonic venturi solves a problem on a pressurized airplane. Here's what the problem is. Let's assume you're flying a pressurized airplane. It has a turbocharger on it, of course, and you're moving the throttle back and forth. Well, the turbocharger is going up and down, creating more or less pressure, but you want a steady flow of air into the cabin of the aircraft for pressurization. How do you get that steady flow of air? You use a sonic venturi. It's a narrow part in the outlet from the turbocharger to the pressurized cabin, forcing the air to go through that narrow part. Bernoulli's law says it's going to speed up as it goes through that venturi, and it will reach the speed of sound. And the speed of sound limits the rate at which air will travel through this venturi. It's called a sonic venturi, and once the air reaches the speed of sound, it will not go any faster unless certain other conditions exist, which we don't have here. And so therefore, you're going to have a steady flow of air. Once you get the speed of sound, the airflow is steady, and what that sonic venturi does on a turbocharged engine is limit the amount of air that can flow through the turbocharger into the cabin for pressurization, giving you a steady flow, and that's a really elegant solution, and it's called a sonic venturi. Now let's talk about power recovery turbines in a turbo compound engine. You say, what in Sam Hill is he talking about now? Well, if you took this turbocharger and took this exhaust gas and spun this turbocharger, you could, instead of driving a compressor with it, just take this spinning turbocharger and connect it to the engine and increase the horsepower out of the engine, because the turbocharger or the spinning turbine can actually have some energy to it. And if you connect this spinning turbine instead of to the compressor, you connect it instead to the engine itself and help the engine out. That is called a turbo compound engine, and that is a power recovery turbine, or for short they'll call it a PRT. They're going to ask you about a power recovery turbine and say, what does it do and how is it driven? Well, it's used on some reciprocating engines, and a power recovery turbine is driven by the velocity of the exhaust gases. And what it does, it drives the crankshaft through suitable couplings, and they're turbines which are driven by the exhaust gas of a turbo compound engine and contribute to the total power output. Now let's talk about some more things they want you to know for the FAA written exam regarding exhaust systems. Let's lead off by talking about augmenter tubes. And by the way, the purpose of augmenter tubes is not to make more noise, although they do a wonderful job of that. They're around the exhaust system. They make the exhaust sound terrific, really big iron type of aircraft. Blah, 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 blah. It sounds great, and it annoys the neighbors an awful lot. But the purpose of an augmenter tube is to use this exhaust air, which is high velocity coming out of the exhaust system, to suck in more air through the engine to cool the engine off. Let's take a look at how it works. What happens is you have high velocity air coming out of the exhaust system, and it goes through a tube, and you can see Bernoulli's principle at work here. It creates a low pressure area here at the rear of the lower end of the engine cowling that sucks more air through the cowling and therefore cools the engine off. How is all that done? That's done with an augmenter tube. A great idea. Now let's take a look at the exhaust system for a turbocharged engine. This happens to be a Cessna 421. You see you have the exhaust manifold going back here to the turbocharger. And of course the exhaust spins that turbocharger. And the fact that that turbocharger is in the exhaust increases the pressure on the exhaust system and thereby increases the temperature on the exhaust system. So the thing you need to know is turbocharged engine exhaust systems operate at higher temperatures and higher pressures. Because of these high temperatures, you need to have a little fancier materials to build the exhaust system out of. So when you have these high pressures and temperatures, like in turbocharged engines, very often they use high nickel chromium steel. In addition to being able to take the high temperatures, this high nickel chromium steel is corrosion resistant and has low expansion coefficient. It doesn't expand and contract as much as normal exhaust systems. Now, you're an old pro, so let me ask you a question that you'll know the answer to from experience. Do you think exhaust systems ever crack and separate and cause leaking? You bet they do, and the FAA refers to these as exhaust system failures. They're going to ask you what causes exhaust system failures. Well, most exhaust system failures result from thermal fatigue cracking in areas of stress concentration, and this condition is usually caused by high temperatures at which the exhaust system operates. So what you need to know for the test is, son of a gun, these things get hot. They have cracking, and that's called exhaust system failures from thermal fatigue. And so if you're flying at night, you have this insidious thing happen to you, like the back of the head sneaks up on you, you could be having carbon monoxide poisoning. You may be not flying at night at all. Your vision just gotten very, very bad because of carbon monoxide poisoning. All right, so if you have an undetected exhaust system leak in a reciprocating powered airplane, it could lead to pilot incapacitation. Now, I don't know how I recognize pilot incapacitation, have it all the time, and it's from carbon monoxide poisoning or gas entering the cabin. So as a mechanic, what are you going to do about all this? Well, you're going to inspect the exhaust system. That's what you're going to do. It's not the way they're going to ask you questions on the FAA written exam. Let's talk about the way they're going to ask you questions about this on the FAA written exam. Here's one. The exhaust system on aircraft using a jacket around the engine exhaust as a source of heat should be visually inspected frequently. And operational carbon monoxide detection tests should be performed periodically. They're saying check for carbon monoxide gas inside the cockpit. Here's another one. An aircraft that utilizes an exhaust heat exchanger as a source of cabin heat, that's it, should have the exhaust system inspected with the heater air shroud removed. So they're saying take off this shroud every now and then and look at the exhaust system itself. All right, reciprocating exhaust system leaks are a bad thing. And so how do you tell when you have an exhaust system leak? Well, you might see soot. That's a question on a test. You can detect exhaust leaks by signs of exhaust soot inside the cowling and on adjacent components. So if you see soot around here, tells you might have an exhaust system leak. You know, there's a tremendous amount of heat coming out of these cylinders of the engines, and the purpose of the exhaust system is to take that heat and move it away along with the exhaust gases. Well, how do you attach the exhaust system to the cylinder around so much heat? Well, obviously you can't use any kind of attachment nut. In fact, what you have to do is use brass or heat-resistant nuts. Not just any old nut that you can find in the toolkit will do. Brass or heat-resistant nuts. Also, you know, there's a lot of expansion and contraction in an exhaust system because it heats up or cools down. So you have slip joints installed very often, and they're required in most exhaust collector systems because of expansion and contracting caused by high heat and cooling. So very often you'll have slip joints. What's the purpose of a slip joint in an exhaust collector ring? Well, it aids in alignment and absorbs expansion. That makes a lot of sense. Let's you and I take a look at a muffler. Now, if you have a muffler, inside this muffler, you know the way they muffle sound is by putting baffles, little plates with holes in them. Now, they're saying if one of these baffles becomes loose, and on the test they say dislodged, on a small reciprocating engine, it may obstruct the muffler outlet, and it could cause excessive exhaust back pressure. So if you have a baffle become loose, it could block off the exhaust and you have too much back pressure. So what do you do about it? Well, there is an exhaust outlet guard inside the muffler to prevent dislodged muffler baffles from obstructing the muffler outlet. They put a guard on here to keep the baffle away from the outlet. That's how you do it, and it's called an exhaust outlet guard. All right, now, super mechanic, we need to know about the characteristics of a good gas weld on exhaust stack. So a good gas weld on an exhaust stack, this is hard for me to say, I'll tell you that, should taper off smoothly. It should be smooth and should taper off smoothly into the base metal. How do you look for a good weld? It tapers off smoothly into the base metal. All right, corrosion-resistant parts such as exhaust collectors should be blast cleaned using sand, which has not been previously used on iron or steel. So if you're going to blast clean exhaust parts, use sand that has not been previously used on iron or steel. Why? Well, sand which has been used on iron or steel might have little particles of metal trapped in it, and these particles can become embedded in the parent material, that's this metal right here, and alter its corrosion-resistant qualities. Because of the corrosive gas going through here, because of the tremendous heat, the corrosion-resistant qualities of the exhaust system metal is very important. Now, by the way, this is the same type of problem that you have if you use galvanized or zinc-plated tools. You don't want to do that on an exhaust system. Or if you mark the exhaust system with a lead pencil. If you mark this with a lead pencil, the corrosion could form right at that particular spot. Also, if you have a sloppy weld in here and the weld protrudes into the inside of the exhaust system, that might cause a local hot spot. And so local hot spots, they say, may be caused by repairs or sloppy weld beads which protrude internally, and they are not acceptable. They also say, why do you have ball joints in reciprocating engine exhaust systems? And the answer is to allow movement. And how loose should they be? Loose enough to permit some movement. So if you have a ball joint in an exhaust system, it's there to permit movement because of all the heating and cooling and expanding and contracting and the engine moving and so on. Can you repair exhaust system components in the field? Well, it's not recommended, according to the FAA, that you repair exhaust system components in the field. Also, how do you clean ceramic-coated exhaust components? Well, if you do have ceramic-coated exhaust components, they should be cleaned by degreasing. And once again, lead pencil marks shouldn't be used because they can cause corrosion right there. Now let's you and I talk about thrust reversers on a jet engine. And I know you thought you'd never ever see it, but here it is. Here's a question that makes sense on an FAA written exam. They're going to say, what is the function of a thrust reverser on a turbojet engine? And the function is to reverse the flow of exhaust gases. That makes sense, doesn't it? All right. The most common types of thrust reversers on turbine engine-powered aircraft are two types: mechanical blockage and aerodynamic blockage. And that's a test question for you right there. Let's take a look at each of these types. First of all, the mechanical blockage, a good example is these clamshell doors. Normally, they're stowed out of the way, but when you want reverse thrust, they come down like so, and the exhaust hits those clamshell doors and reverses itself. That's a good example of a mechanical blockage thrust reverser. Let's take a look at an aerodynamic blockage device as a thrust reverser. And this is the bypass duct on a jet engine. And when you want reverse thrust, these aerodynamic fins move down. They have a little aerodynamic shape to them. And the air comes along and hits those fins, and the aerodynamic shape bends the air and reverses the thrust. And that's an aerodynamic blockage type thrust reverser. Now, the aerodynamic blockage type of thrust reverser system normally makes use of what is known as cascade vanes. Now, let's take a look at how they work. Normally, the thrust goes right through the engine, and of course, it goes right through the bypass duct of the engine, right through the exhaust of the engine. But when you want to reverse the thrust of the engine, what you do is you block the bypass duct, you block the exhaust system, and then the air is forced in the bypass duct to go through cascade vanes. These cascade vanes are like louvers that redirect the air forward, and the same thing happens in the core system very often, and that directs the air forward. So they're going to ask you on the test, what is the purpose of cascade vanes? And the purpose is to turn the air forward after it's been blocked, and it's air that would have gone through the bypass duct and or the exhaust system. Now, if you have a high bypass turbofan, as we might have right here, you know that much of the thrust of this engine comes from the bypass duct. So you can get away with reversing only the bypass duct in a high bypass turbofan, or you can, and that's the cold stream, by the way, the bypass duct, or you can reverse them both. But you can get away with only reversing the high bypass duct because it's a high bypass fan, and that's where most of the thrust comes from. Now, how do you move things around in a thrust reverser system? How do you change the clamshell doors, put in the blockage, and so on? And there's three systems that you could use, three methods you could use to power these things. You could power thrust reversers by electricity, hydraulic pressure, or pneumatic pressure. Now, if you use pneumatic pressure, where would you get that pneumatic air from? Well, normally the engine bleed air system. The whole idea of thrust reversers, you have this great big hunk of metal and you're landing, and now after you land, you'd like to get this thing stopped without too much wear and tear on the brakes. Well, that's not very efficient, because what you're doing is taking these engines that are designed to move the airplane forward, now reversing everything and trying to use those same engines to stop the airplane. Well, the engines work a lot better going forward than rearward, so the rearward thrust capability of an engine in the thrust reverser system when it's deployed is less than its forward capability, quite a bit less. How much less? Well, it's down to about 35 to 50% of the rated thrust in the reverse direction. It's a lot of help, but it's not as efficient as going forward, but I wouldn't want to do without it. Now let's take a look at what the pilot does inside this aircraft to use reverse thrust. Now the first thing you do, and this is very important, is you retard the throttles to ground idle. There are other answers that say advance the throttles. Advancing the throttles when you're trying to stop the aircraft is not a wise thing to do. So you're going to get the answer right off if you retard the throttles is the first thing, and that'll get you the right answer on the test. Now the next thing you want to do is reach over the throttles, and there's levers here on the front side of the throttles, and those are the reversed thrust levers. You pull up on those levers for the amount of reverse thrust that you want. Now, when you got the airplane at the speed you want, you push down on those levers again, and that is retarding the thrust reverse levers to ground idle. And you want to do all this at or above a minimum specified speed. If you do it too slow, you can get dirty air into the intakes of the engines, and that's bad. So that's how you operate these levers inside this cockpit for reverse thrust. Now, you can, in some cases, actually use reverse thrust to back the airplane up on the ground using reverse thrust. It is not considered to be a good idea. It is, in fact, considered to be done, something to be done with great caution, because operating thrust reversers at low ground speeds can make you pick up sand and other foreign objects, so you can get foreign object ingestion. And also the hot gases can come back into the engine, so you have hot gas re-ingestion. That's considered to be a bad thing. And also the air from the exhaust gets up to the front of the engine and confuses the air at the front of the engine. That can cause compressor stall. So using reverse thrust on the ground is something to be done only with great caution. Now, believe it or not, you and I have just covered everything FAA wants you to know about induction and exhaust systems, and now you can see how a simple thing like an exhaust system can cause something magnificent like this to happen.